Hello viewers, in today's session we are going to discuss some simple problems related to exact differential equations, right? So before solving the problems related to exact differential equations, let us quickly see the definition of exact differential equation of first order and first degree, and let us see the condition for which the given differential equation is said to be an exact differential equation. So here we are going to discuss exact differential equations of this form, that is say mdx plus ndy is equal to 0, right? So here we are going to solve exact differential equations of this form, and the definition of exact differential equation, it goes like this: a differential equation which can be obtained from its primitive, that is its solution by simple differentiation and without any further say operation of elimination or reduction, is called an exact differential equation. Or in other words, we can also say that an exact differential equation is formed by equating an exact differential to 0, right? So here we'll solve problems of this form, and here the necessary and sufficient condition for the differential equation of this type to be an exact differential equation, if we have this condition, that is the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x, right? So this is the necessary and sufficient condition for this equation to be an exact differential equation. So let us now solve some problems. So let us solve this problem. So here we are going to discuss the algorithm or the procedure how to solve exact differential equations of this form, right? So here we have this differential equation, that is x raised to 4 minus 2y dx plus y cube minus 2x dy is equal to 0, right? So now if we compare this equation with this one, then the value of m is given as x raised to 4 minus 2y. So this is m, and here we have a dx, and then we have n, right? So n is given by y cube minus 2x, right? So let us first see whether this given equation is an exact differential equation. So let us first verify this condition for this equation. So we have del m over del y is equal to del n over del x. So let us first find out the partial derivative of m with respect to y. So del m over del y is given by del over del y. Here we have x raised to 4 minus 2y. Now see, here we have x raised to 4, and this term does not contain any y. So the derivative of x raised to 4 with respect to y is 0, because here we are dealing with the partial differentiation. And then we have minus 2, and the derivative of y, partial derivative of y with respect to y. So we have 0 minus 2 times 1, and that is minus 2. And here we have to find del n over del x. So we have del over del x, and here we have y cube minus 2x, right? So here now if we find out the partial derivative of y cube with respect to x, then we see that here this term y cube does not contain any x. So the derivative, the partial derivative of y cube with respect to x is 0, and then we have minus 2 del over del x of x, and here we have 0 minus 2 times 1, that is the derivative of partial derivative of x with respect to x is 1, so we have a minus 2. So here we see that this condition is satisfied for this differential equation. So we can now claim that this equation is an exact differential equation of this type. Mdx plus ndy is equal to 0. So here we have del m over del y is equal to del n over del x, and both these partial derivatives are equal to minus 2. So this equation is an exact differential equation. So let us now see the algorithm how to find out the general solution of this exact differential equation. So now the first step to get the solution of this equation, we have to integrate m with respect to x, right? And here when we integrate m with respect to x, then we keep y as a constant, right? So here we have the integral, and m is x raised to 4 minus 2y, and here we have dx, right? So when we integrate m with respect to x, then we keep y as a constant, right? So here we have now integral x raised to 4, here we have dx, then we have minus 2 y, and integral dx, because here we are keeping y as constant, so we can take 2y outside the integral, right? So we have now the integral of x raised to 4 is x raised to 5 over 5, and here we have minus 2y, and here the integral uh, dx is simply x. So we can now write x raised to 5 over 5 minus 2xy, right? Okay, now the next step is to integrate n with respect to y, that is we have to find this integral n dy. So n is y cube minus 2x, and here we have dy, and when we integrate n with respect to y, then in this case we keep x as constant, right? So here we have now integral y cube dy, then we have here 2x and integral dy, because here we are taking x as a constant, so we can take 2x outside the integral. So now here we have y raised to 4 over 4, and here we have minus 2x, and the integral dy is simply y, right? So here we have used this result, that is integral x raised to n dx is x raised to n plus 1 over n plus 1, where n is not equal to minus 1, right? So now we have the integral m dx is equal to x raised to 5 over 5 minus 2xy, and integral n dy is y raised to 4 over 4 minus 2xy. So now to write the solution of this differential equation, we have to keep one important thing in our mind, right? Now see, when we have the integral m dx, we have this expression, and when we have this integral n dy, we have this expression, right? And if we look at these two expressions, then we can see that this term, that is minus 2xy, and here we have minus 2xy. So this term, that is minus 2xy, is appearing in both the integrals, right? So here, to write the solution of this differential equation, we have to consider this term, that is minus 2xy, only once, right? Because this term is appearing in both the expressions or in both the integrals. So to write the solution of this differential equation, we have to now add these two expression, taking this term minus 2xy only once, and will equate the sum to a constant, right? So the solution is now x raised to 5 over 5, and then we have here minus 2xy. We will consider on this term, that is minus 2xy, only once, and here we'll take only this term, that is y raised to 4 over 4, and will equate this expression to a constant, say c. So this is the required solution of this exact differential equation. So now consider this problem. Here we have to solve this equation: 2x square plus y square dx plus 2xy dy is equal to 0. So let us first compare this equation with this one. So the value of m is 2x square plus y square, and the value of n is 2xy. So let us first verify that this given equation is an exact differential equation by equating these two partial derivatives. So here del m over del y is del over del y. Here we have 2x square plus y square, and here we have 2 times the derivative of x square with respect to y. Here we have del over del y, and here we have a y square, right? So here this term is 0, because the derivative, the partial derivative of x square with respect to y is 0, and here we have simply 2y. So here we have 2y. Now let us find del n over del x. So this is del over del x, and here we have 2xy. So here when we find the partial derivative of 2xy with respect to x, we take y as constant, and in this case we take x as constant. So this derivative was 0, and here we have 2y, and the derivative of x. So this is 2y times 1. The derivative, the partial derivative of x with respect to x is 1. So here we have 2y. So now we can see that this condition, that is del m over del y, is equal to del n over del x, and here both these partial derivatives are equal, and the common value is 2y. So this suggests that here this given differential equation is an exact differential equation. So let us now find out the solution of this equation. So now the first step is to integrate m with respect to x, and here we'll take y as a constant, right? So we have m as 2x square plus y square, and here we have dx, and when we find the integral m dx, then we take y as a constant, right? So here we have now integral 2x square dx, and then we have integral y square dx, and here we can take 2 outside the integral, and we have here since we are taking y as constant, so we can take y square outside the integral, and here we have 2 times x cube over 3, and here we have y square times x, the integral dx is x. So we have now 2x cube over 3, and here we have xy square. So now let us find out this integral n dy. So when we find out integral n dy, then we take x as constant. So we have integral, and n is 2xy. Here we have dy. Now since x is we are taking x as constant, so we can take this 2x outside the integral. We have y dy, and we have 2x, and here we have a y square over 2. Now this 2 and this 2 get cancelled, and we have xy square. So the integral n dy is equal to xy square. So now we see that the integral m dx is given by this expression, and integral n dy is given by this expression. And if we look at this expression and this expression, then we can see that this term, that is xy square, it appears in both the expressions, right? So to write the general solution of this differential equation, we will add these two expressions, but taking xy square, that is this term, only once, right? Because here xy square, this term is repeating, so we'll take it this term only once. So the general solution is now given by 2x cube over 3 plus xy square, and the sum is equated to a constant, say c. So this is the general solution of this exact differential equation, right? So when we find out the integral mdx, we get some expression, and when we find out the integral ndy, we get some expression, right? So when we have to write the general solution of the given differential equation, then we have to retain only those terms which are not repeated, right? So here xy square is repeating over here, so we'll take it only once, right? So adding these two terms, and the sum is equated to some constant, say c. So now consider this differential equation. So here we have to solve 1 minus 2xy minus y square dx minus x plus y whole square dy is equal to 0. So comparing this equation with this one, the value of m is 1 minus 2xy minus y square, and n is given by negative of x plus y whole square, and this can be now written as expanding it with the help of the identity a plus b whole square. We have x square plus 2xy plus y square, and multiplying these terms by negative sign, we have minus x square minus 2xy minus y square, right? So now let us find out del m over del y. So we have del over del y, and here 1 minus 2xy minus y square. Now the derivative of 1 with respect to y is 0. Then we have minus 2x del over del y, and here we have y, and then we have del over del y and y square. So here we take x as constant, right? So here we have minus 2x, and here we have 1, and here we have minus 2y. So this is minus 2x minus 2y, right? And here we can now find del n over del x. So this is minus del over del x. Here we have x square, Then we have minus 2y del over del x, and here we have simply x, and here the derivative of y square with respect to x is 0. So here we have minus 2x, here we have minus 2y times 1, and here we have minus 0 because here we take y as constant. So here we have minus 2x minus 2y, and from these two expressions we can see that del m over del y is equal to del n over del x. That is, this condition is satisfied, right? So this equation is an exact differential equation because here the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x, right? So this condition is satisfied. So let us now find out the solution of this differential equation. So let us now first find out the integral m dx. So we have integral 1 minus 2xy minus y square and dx. So writing the value of m, and here we can now write 1 dx, then we have minus 2y integral x dx, and then we have minus y square integral dx. So here while finding out the integral m dx, we take here y as constant, right? So here the integral 1 dx is simply x, and here we have minus 2y. Integral x dx is x square over 2. Here we have minus y square, and here we have x. So 2 and 2 get cancelled. We have x minus x square y minus, and here we have x y square. So now let us find out the integral n dy. So n is minus x square minus 2xy minus y square, and here we have dy, and while calculating integral n dy we take x as constant. So here we have integral minus x square dy, then we have minus integral 2xy dy, and minus y square dy. So here we are taking x as constant, so we can take x square outside the integral. So we have minus x square integral dy. Here we have minus 2x outside the integral, we have y dy, and then we have integral y square dy, right? So we have minus x square, here we have simply y, here we have minus 2x y square over 2, and here we have y cube over 3. So here 2 and 2 get cancelled, so we have minus x square y minus xy square and minus y cube over 3, right? So we have now obtained integral m dx as x minus x square y minus xy square, and integral n dy as minus x square y minus xy square and minus y cube over 3, right? So now the general solution of this differential equation can be written by taking the sum of these two expressions and then equating the sum to some arbitrary constant, say c. But here we can see that this term, that is a minus x square y minus xy square, is appearing in both the integrals, right? So we have to consider this term, that is a minus x square y minus xy square, only once, because this is a repeating term, right? So the general solution can be now obtained as here we have x, then we have minus x square y minus xy square, and then we have this term. So here we have minus y cube over 3 is equal to c, where c is some arbitrary constant. So the general solution of this differential equation is given by x minus x square y minus xy square minus y cube over 3 is equal to c, right? So here what we have done so far, see, we have calculated here integral mdx, then integral ndy, and we have added both these terms, and the sum is equated to some arbitrary constant c. But here we have to keep one thing in our mind while writing the solution. We have to consider the repeating terms only once, because here we have minus x square y minus xy square. This term is appearing in both the expressions, so we have to, or we this term has to be considered only once in the solution, right? So the solution can now be written as x minus x square y minus xy square minus y cube over 3 is equal to c. So here we have x, then we have minus y cube over 3, and these two terms, that is this entire term minus x square y xy square, is repeating in both the expressions, so we have to consider it only once, right? So this is the required solution. So let us now consider this differential equation. Here we have 1 plus 4xy plus 2y square dx plus 1 plus 4xy plus 2x square dy, right? So let us compare this equation with this one. So here the value of m is 1 plus 4xy plus 2y square, and the value of n is 1 plus 4xy plus 2x square. So first we'll find out the value of del m over del y. So del over del y, and here we have 1 plus 4xy plus 2y square. So here the derivative of 1, partial derivative of 1 with respect to y is 0. Then here we have 4x, because while finding out the partial derivative of this expression with respect to y, we take x as constant. So we have del over del y, here we have y, and then we have 2 times del over del y and y square. So here we have 4x times 1, and then we have 2 times 2y. So this is 4x plus 4y. So let us find out del n over del x. So this is del over del x. Here we have 1 plus 4xy plus 2x square, and the derivative of 1 with respect to x, this is 0. And while finding out the partial derivative of this expression with respect to x, we take y as constant. So we have 4 y, then we have del over del x, here we have x, and here we have 2 times del over del x, and here we have x square. So here we have 4y times 1, and here we have 2 times 2x, and this is 4y plus 4x, and this is 4x plus 4y. So these two expressions are same. So we conclude that this given differential equation is an exact differential equation, because it satisfies this condition, that is del m over del y is equal to del n over del x, that is equal to the common value is 4x plus 4y. So let us now find out the solution of this differential equation. So first we find the integral m dx, right? So here the value of m is 1 plus 4xy plus 2y square. Here we have dx, and while finding out the integral of this expression with respect to x, we take y as constant, and here we have now 1 dx, then we have here integral 4xy dx, then we have integral 2y square dx. So this is x, and here y is taken as constant, so we can take 4y outside the integral. Here we have x dx, here we have 2y square outside the integral, because this is taken as constant, so we have dx. So this is x plus 4y. Here we have x square over 2. Here we have 2y square. Here we have x. So this is x plus here we have 2, so this is 2x square y, and here we have 2x y square, right? So now let us find out the value of the integral, that is n dy. So here we have the value of n as 1 plus 4xy plus 2x square, and here we have dy, and while finding out the integral of this expression with respect to y, we take x as constant, right? So now here we have integral 1 dy, then we have integral 4xy dy, and here we have integral 2x square dy. So here we have simply y, here we can take 4x outside the integral, this is being constant, and here we have y dy, and here we can take 2x square outside the integral because this is a constant, and here we have integral dy. So we have y plus 4x times y square over 2, then we have 2x square, and here we have a y. So here we have 2, so this is y plus 2xy square, and here we have 2x square y. So the integral n dy is given by y plus 2x y square plus 2x square and y, right? So now if we look at these two expressions, then the solution of this differential equation can be obtained by taking the sum of these two expressions and then equating the sum to some arbitrary constant c, and here we can see that this expression, that is 2x square y, here we have 2x square y, here we have 2x square y, here we have 2xy square, and here also we have 2x y square. So this expression is appearing in both the integrals, right? So we have to consider this expression only once. So this has to be considered only once while taking the sum of these two expressions, and then the sum is equated to some constant c. So the solution is now given by x plus y, and here we have x plus y, and then this term is considered only once. So here we have 2x square y plus 2xy square, and here we write the arbitrary constant c. So this is the required solution of this differential equation, which is an exact differential equation. So here, let us summarize the algorithm, that is the procedure for finding out the solution of this form of exact differential equations. Mdx plus ndy is equal to 0. So first we take m and n, and then we verify whether this condition is satisfied by the given differential equation. And once it is achieved, that is this condition is satisfied by the given differential equation, we claim that the given differential equation is an exact differential equation. And then comes the solution of the given differential equation. We first find the integral mdx, and then we find the integral nty, right? So first we perform the integration of m with respect to x regarding y as a constant, and then we perform the integration of n with respect to y, and taking x as constant, and will retain or will collect only those terms which are not already obtained, or which have not been already obtained in the integration of m, right? And then we take the sum of the expressions, that is the integral of mdx and integral of ndy, and the sum is equated to some arbitrary constant, and the resulting expression gives us a solution of the given differential equation, right? So here we see that 2x square y plus 2xy square is repeating in both the expressions, so we'll retain this term only once, right? So we have x plus y plus 2x square y plus 2xy square is equal to c, which is the required solution.